what was in last couple of lectures. So basically, I have shown how to use the formalism of orthogonal polynomials, and using this formalism, I have shown how to get the level density correlation function for the unitary ensemble for beta equal 2, and it appears to be a very simple form like this, and then this picture illustrates how this form, which is orange dashed line, how it fits the exact expression which was obtained using the orthogonal polynomials. So this is some approximate expression when the size of matrix goes to infinity, but already at the size of 200 there is almost no difference between the exact blue formula, which is more complicated and which holds for any n, could be even n equals 2. So what I wanted to illustrate that already at n equals 200, this simple formula that corresponds to n equal infinity fits very well the exact one. But then beforehand we discussed the so-called plasma model, classical plasma with logarithmic interaction, and we obtained also a sort of approximation to the same density of level correlation function, and within the plasma model it is this red lines, and it is seen that what plasma model misses, it misses the oscillations with the period of mean level spacing, and it actually passes through the middle of this oscillation, so it gives it is obtained from this formula if I average sine squared over such oscillations. And we know that the average of sine squared is 1/2, and therefore we are here in the middle. So then next I have shown to you the corresponding formulas for the level density correlations in the case of orthogonal ensemble and the symplectic ensemble. And important thing is that it is expressed in terms of the same kernel, but in addition to this term, which is for beta equal 2, we have two other terms which are looking symmetric in some sense, and when we substitute here the Wigner-Dyson kernel, which we derived from orthogonal polynomials, and then find the asymptotic form of this at large separations between the energies, then we will get these three expressions which is without this unity and only the other part, which is called y cluster function. And what we see that there is this non-oscillating part which we obtained from the plasma model, and then there is an oscillating part which falls down as a power law, and this power is different for orthogonal unitary ensemble, but in symplectic ensemble we have two harmonics of the oscillations, and this is related with with the Kravtsov degeneracy, which I discussed last time. So also this formula can be viewed like the zero energy form of the density of fermions with and without interaction, and such form tells you that there is a certain crystal order, because this oscillations is like the oscillations of the density in the crystal, but this crystal order is not long range order because it decreases as a power law. So this is what happens according to the well-known theorem. If we have one-dimensional system at finite temperature, we have very short crystal order. It is practically destroyed very quickly. If we have zero temperature, then in one dimension there is no long-range order, but there is the power law decrease of the corresponding order parameter. And this is what this random matrices also display in some exact form. And then I found the so-called spectrum form factor, which is the Fourier transform of essentially of this correlation function. Also, this R is different from this Y by the presence of delta function, and this delta function leads to the constant when I take a Fourier transform of a delta function, it will be a constant, and for that reason the spectrum form factor for all three ensembles goes to a constant asymptotics at large times, but the difference is that here the asymptotic value is 1 for the unitary and for the orthogonal ensemble, but for the symplectic ensemble it is 2. And this is because of Kravtsov degeneracy, because the delta function in the presence of Kravtsov degeneracy, it has the weight of 2. And now there was some question which Dima asked me, and the question was, okay, so there is this spectrum form factor, very good, you do the Fourier transform, but what about physical meaning of that? Is there at least some mental experiment that can show where this spectrum form factor can show up? Not just computer simulation, but some at least mental real experiment. And in fact, there is an old paper by Prigodin, Schuler, Yefetov, and Ida, where such physical application of the spectrum form factor for Wigner-Dyson theory is discussed. So this is the old paper. As I said, it is the end of 90s of last century, and at that time people there was a boom in micro systems such as quantum dots. So everyone constructed the quantum dot and measured things, and then observe different signatures of the random matrix theory. And at that time, the random matrix theory became known to condensed matter physicists. Beforehand, it was only the instrument of nuclear physicists, but not condensed matter. And so the experiment is that, this is in principle can be done as a real experiment, but this is some mental experiment. So you have a quantum dot and you inject an electron at some point, and then you probe the electron density in a different point. And you ask a question, what will be the, how this density which is injected here, how it will depend on time in this point at a distance r. And actually what is the prediction of this paper is the following, that when you inject this particle, then there are two stages of evolution. Actually, three stages of evolution. For very short time, when this is really times like 10 to minus 12, this is ballistic motion of ballistic spreading of this electron. Ballistic because for such short time, which is smaller than the time of scattering with impurities, the evolution is ballistic. But then there is the second stage where at the times which is much bigger than the time of mean free path, the time of scattering, and then the diffusion is formed. And this diffusion is essentially classical, and what happens in a classical situation, we know that if you create a density at some point, the wave packet in fact, and then initially it is almost entirely concentrated at this point. But then during the classical diffusion evolution, what happens is that this profile becomes wider, so there is a propagation of this extra density, but it becomes smaller because in total there is one particle, and if I integrate this profile over distance, I should always have one particle. So therefore, if it spreads over the distance, it must be lower in the amplitude. But this is the purely classical stuff, which is well known from, I don't know, 18th century. And then in the end, what should happen is that it becomes wider and wider, and at some point it is homogeneously spread over the entire surface of this dot. And at that point, the density becomes just 1 over volume or surface, depending on is it three-dimensional or two-dimensional dot, and it is absolutely homogeneous. So this is what would be the end of the story if there is a classical physics only there. So it would be like like the heat death. So there will be no more evolution, it spread homogeneously and evolution stopped. But in fact, quantum physics does something unexpected, because after this time, the time when the density becomes homogeneous, and this time is of the order of the diffusion time to reach the boundary. So it is so-called Taulis time, the time for which the boundary is reached. Now, if the time is much bigger than this Taulis time, then quantum physics starts to work. And at that point, at that point, this formula, which is derived in this work, starts to be valid, and what is happening according to this formula is the following: that in addition to this one over volume homogeneous part, there is some inhomogeneous part which emerges, and this inhomogeneous part has a form of so-called Friedel oscillation. So the density oscillates at large distance from this point. This form is valid, otherwise it is some basic functions. And these oscillations are with the period of de Broglie wavelength. And this de Broglie wavelength is set by the Fermi momentum. Okay, so there is this Friedel oscillations, which form is here. But there is also an amplitude of Friedel oscillations, and this is this factor, C of tau. According to this work, this C of tau is the spectrum form factor plus some number that depends on the symmetry. So if we are in a unitary ensemble at this stage where time is of the order of the diffusion time, there is only 1 over v, and this gamma is 0. And we know that that every spectrum form factor at 0 time must be 0, and this is the signature of incompressibility of the system of levels. So the fact that the integral of this correlation function is exactly 0 for all three ensembles, and if time is 0, then it is simply an integral, and therefore this is a feature of the Wigner-Dyson ensembles, of all Wigner-Dyson ensembles, that can be traced back eventually to invariance on the basis rotation. Okay, but anyway, so according to this formula, spectral form factor for all Wigner-Dyson at 0 time is 0. But then, so what this means for this formula for the unitary ensemble, where this is absent, so here the time 0 means the time which is of the order of the Taulis time, where this quantum physics of essentially interference at multiple infraction of waves from the boundary when it starts working. And so what happens then to this form is the following, that if I average over these Friedel oscillations, then at the time of the order of the Taulis time, I have exactly 1 over v for the unitary case, and then as time increases, there is a revival. So you know what happens is that in classical physics you just spread homogeneously and stop. in quantum physics, which is reflected by this spectrum form factor, after that there is some evolution. So the system remembers that it was created at a point R, at this red point, and therefore, as time increases beyond this value, then the Friedel oscillations, which I have shown here, become more and more becomes bigger in the amplitude, and this amplitude is set for the unitary ensemble is set by spectrum form factor. So it is quite I mean, at that time it was quite unexpected, because what will happen is that in the unitary ensemble, first we have no correction to the homogeneous distribution, and then the amplitude of Friedel oscillation start to grow, and eventually it reaches unity, and it never falls down. So this memory about the initial position where the electron was created, according to this theory, it remains forever. So this inhomogeneity related with the Friedel oscillations, it remains forever. But forever means the following, that as long as quantum mechanics is working, but we know that quantum mechanics is, I mean, in such real system, it is spoiled by the environment. So there is an environment, there is some noise, and this noise destroys coherence of quantum mechanics, and eventually it destroys all this nice feature of the infinite memory. So this memory becomes finite in real system, but still this feature of Friedel oscillations, it lasts anomalously long. So this was essentially the first, maybe the first examples of what is now called quantum scars. Because what is quantum scar? You create a special quantum initial state, and this special initial state lasts anomalously long. So the inhomogeneity associated with this initial state, it lasts anomalously long. So in main body system, it is a big deal to find this special state for which this anomalously long memory of the initial form will last. In this example of random matrix theory, you don't have to work hard in order to find this special initial state. You create just wave packet at some point, and then as long as quantum mechanics is not destroyed by the noise, so you will have Friedel oscillations, which are the example of such quantum scars. Now we come to more theoretical stuff, and this more theoretical stuff is the following. So I just declared, because I did not derive this formula. Sorry. Okay. I did not derive this formula. I simply took the full formula that follows from. I derived it for the unitary case, but I did not derive it for the other two cases, because this formula is nothing but the long-range asymptotics of the exact Wigner Dyson formula, which I should find, but okay, by these two. So if you take these two exact formula, plug in here the corresponding kernel, you will get this expansion. But I did not derive this. And now what I want to do, I want, instead of derivation, which is quite subtle, and also written in almost all the standard books on random matrix theory, instead of that, I will look at this result, and I will present this result in a form which explains how these different coefficients here, unity here, 2 here, 1/2 here, 2 here, and also coefficients there, how do they emerge? Because there is some order in all these coefficients, they are not just arbitrary. And in order to do that, first of all, I noticed that this formula can be obtained if it can be written in a form of some correlation function of free bosonic field. So you see this formula I said, so it is obtained just by orthogonal polynomials, blah blah blah. Nothing about bosons, nothing about fermions. But when I look at it carefully, I will show now for you that all this, that this G is essentially the Green's function of the free bosons at zero temperature. And now, and this is a very far-reaching analogy, because as I told you in the beginning of our lectures, that the Wigner-Dyson theory corresponds to the ground state of some system, of some model of interacted fermions, which is known like Calogero-Sutherland model. So then, essentially, all these oscillations are nothing in this language like an oscillations with the in the system of fermions with K Fermi is equal to pi. So the fact that there are such oscillations is easy to understand if we invoke this analogy with fermions. But then, what is known in addition, it is known that, I show you this model once again. Yeah, this is this model of Calogero-Sutherland, so it is quite a weird model, because there is an inverse, there is a singularity here, there is an inverse square interaction between the bosons, the fermions, and there is an interaction constant which becomes 0 when beta is equal to 2 in the unitary ensemble. But if we are in orthogonal ensemble, it is negative, which means that there is attraction. And when we have beta equal 4, a symplectic ensemble, it is positive. This means that on the top of fermionic repulsion, there is some more repulsion. And this is a very remarkable model because this is essentially a model of which has many features of quantum Hall state and such things like synthetic emergent particles with intermediate statistics, which is neither fermion nor boson. So you start by fermions, but then there is, and these fermions remain fermions when beta is equal to 2, but when there is interaction in one dimension is extremely relevant, and it makes completely scrambles the initial fermion to the point that the excitations are no longer fermions, but they are instead anyons. So the particle with this is why this model is a whole story about studying this model in mathematical physics. But what is important that this model also describes the ground state of this model, describes it is equivalent to Wigand-Dyson theory if beta is equal to 1 or 4. So, but when this model was studied, along with a number of other one-dimensional models, interacting models, it was realized that in one dimension there is no the barrier, the infinite barrier between fermions and bosons. So the thing is that if you have a one-dimensional interacting system, then the only excitations that you can have there is the variation of the density of particles. And variation of the density of particles is like sound, and sound waves are bosons, and therefore it was a remarkable discovery that one-dimensional fermion system with interaction, they behave essentially as bosons. And then what means they behave as bosons? This means that you can express various quantum mechanical averages for such model in terms of bosons, of the corresponding correlation function of the bosonic field. So, moreover, it appears the following, that the interacting fermions is difficult to study, because any interactive system, if you start from non-interacting one and do the perturbation theory, it is a long way to describe real properties of such systems in one dimension. But if you represent the observable, the correlation functions, in terms of the bosonic operators, then it appears that the corresponding field, the corresponding action of the bosonic field is a free action. So you have interacting bosons, but they are equivalent to non-interacting, interacting fermions, but they are equivalent to non-interacting bosons. And this is what I partially demonstrate today. So, okay. So, what I said, that this correlation function can be expressed in terms of some correlation function of free boson field, which is quantum field, and therefore it depends on the time and on the coordinates. So it is 1 plus 1 theory. And if it is Wigner-Dyson, then it should be a ground state of such field. So the temperature should be equal to 0, because this is an imaginary time, in the action, it is the integration from 0 to 1 over temperature. Okay, so now I start to show. So basically, this is the mappings which I am talking about. So you have a Wigner-Dyson theory, and it can be considered as a pure mathematical stuff without any reference to any physics, boson, fermions, nothing, just mathematics. But then we know that it is equivalent to this to this Kalosher-Sutherland interacting fermions, to the ground state of this Kalosher-Sutherland interacting fermions. But then this model is exactly solvable by so-called beta ansatz, and so it is solvable exactly by mathematical physics methods. But what is more important, it is important that if you are interested not at short distances, at small times, but you are interested in large distances and large times, then it could be reformulated as in terms of the bosonic field, which I have shown to you, and this is known as the Latinger liquid. So essentially, what is Latinger liquid? It is the limit of quantum one-dimensional system at large distances and large times. So large time, large energy times small temperatures. Then actually such type of Latinger liquid can be obtained not only from Kalosher-Sutherland model, but practically of a very big variety of different models which are looking differently when they are considered at small distances and small times, but at large distances and large times they become all the same, and the only point that controls which has a memory of the initial model is this parameter k, which should be computed each time for each particular model. So for the Kalosher-Sutherland model, we will find this constant. So okay, so then you see there is the quantum analogy, then this one-dimensional interacting fermions are generally represented as a bosonic theory, and for this Wigner-Dyson case, this is a bosonic theory at 0 temperature.
Vladimir, when you're saying that this Latinger liquid is only, so it was my understanding that the second arrow to the Latinger liquid we can only map if we are interested in long times. Long times correspond only to the short spacings.
Long times, here long imaginary times. If we are talking about thermodynamics, this means low temperature. Because you see, the thing is that if you consider thermodynamics, then you switch to imaginary time. And and then the integration of this imaginary time goes from 0 to 1 over temperature. So this is the way it is very well known actually when you may consider dynamics in real time, and you may consider thermodynamics, and it means it appears that they are very easily connected. So if you want to obtain thermodynamics out of dynamics, all what you have to do, you have to consider imaginary time and say that this imaginary time goes only up to 1 over T, where T is the temperature. So if vice versa, if you have a theory in the imaginary time, then you can make an analytic continuation and get a real to the real axis and have the dynamics, the real dynamics. So these things, the thermodynamics and dynamics, they are related very essentially by analytic continuation. So this is unfortunately goes well beyond of what I'm going to discuss here, but this is a matter of the usual knowledge. So there is you see, if you have this restricted integration of imaginary time, you can do the Fourier transform, but you cannot do a Fourier transform, usual Fourier transform. If your time is restricted, that means that your frequency must be quantized, and so appears so-called Matsubara frequency, which is 2 pi T times n for bosons, and Matsubara frequency is 2 plus 1, 2n plus 1 plus 1 pi T for fermions. So in this way you can your theory becomes your thermodynamics becomes the theory in terms of such discrete frequencies, but then if you make an analytic continuation to what you have to do, I mean, you may say that there is I omega and put imaginary unit here, and then you have some discrete you know your correlation function in some discrete points of the of this is in omega and this is re omega, and then what you have to do in order to find your dynamics, you have to analytically continue your function from these points to the entire real axis, and then you have real dynamics. So this is something which is very well known, but unfortunately I cannot stay longer here. So this is imaginary time, because I'm considering the correlation function in the thermodynamic ensemble. So, okay, so now I want to make some calculations in order to convince you that this can be obtained from such an action. So what is important to know, as I said, different one-dimensional models with interaction lead to the theory similar to that, but with different constant k. And in general, if k is equal to 1, this means this theory is equivalent to 3 bosons, to 3 fermions. So this is a bosonic theory, these are free bosons in all the cases, in cases of attraction, repulsion, no interaction between fermions. So bosons, this bosonic action is always quadratic, it is three bosons. But the memory about the initial model of fermions interacting or non-interacting is in this K. So when K is equal to 1, this bosonic action corresponds to non-interacting fermions. When K is smaller than 1, it corresponds to fermions with repulsion. And when it is bigger than 1, it corresponds to fermions with attraction. So this is very general stuff, which is not only for the bosonization of the Colosio-Sutherland model, but many other models lead to the same theory. For instance, the models of hardcore fermions, which okay. So then what is very important, why this representation in the form of boson field is a big progress. It is because interacting fermion systems can be represented as non-interacting bosons. And of course, to treat non-interacting bosons is, as I will show now, it's a very simple thing. And to treat by perturbation interaction in one-dimensional system, it is a nightmare. And basically what, since I told you about Lagrangian liquid, I tell you why, what is the difference between the Lagrangian liquid of fermions and the Fermi liquid of fermions, which on down Fermi liquid theory. So what we know about Fermi liquid? We know that, let us consider the occupation number as a function of momentum. And for free fermions, we know what happens. So there is at zero temperature. We know what happens is that there is a Fermi step. So the occupation number is 1 for if momentum is smaller than the Fermi momentum, and this is Fermi C, and it is 0 otherwise. And these are non-interacting fermions. So now what Landau taught us is the following, that if you have an interacting fermions in, let's say, 3 dimensions, then this thing is spoiled, but not completely. So basically we have the following, we have unity. We have also Fermi momentum. When momentum is much smaller than the Fermi momentum, then we have unity. But then when we approach the Fermi momentum, this occupation number is decreasing, but to some finite value. And then when it is bigger than the Fermi momentum, it also starts from some finite value and then goes to 0. But there is always a jump here. And this jump is the feature of the Fermi liquid. This is the feature, the remnant of the step here, which was for non-interacting Fermi particles. So Landau said essentially that if you have interacting Fermi particles, in some sense they can be qualitatively considered as non-interacting. First of all, because there is a Fermi momentum. Second, because there is a jump. And then people start to study experimentally, theoretically, various situations and found that in fact in 1D and also sometimes even in 3D, this is not the case. So that the Fermi liquid theory doesn't work. Now, the problem for 3D and even for 2D, why it doesn't work, how to get it theoretically, it is still open. So there were trillions of people working for 50 years, no problem, almost no problem. But in 1D there is a great progress, and this progress is related with the Lagrange liquid, with the so-called bosonization of the Fermi system, one dimension. And what happens, what was shown, that again there is a Fermi, the notion of the Fermi momentum remains, but what happens is that here, instead of the jump, there is a parallel singularity, a branch singularity, and here too. So this jump collapses, and instead you have a branch singularity, and this is the signature, this is the, I would say, the concentrated picture of the Lagrange liquid. And basically, such picture appears in a variety of one-dimensional interacting systems.
Isn't that just equivalent to finite temperature for the non-interacting fermions?
Not really, because in qualitatively, yes, qualitatively we know that if there is a finite temperature, then there is a smearing here, but what happens at finite temperature is, of course, the jump disappears at finite temperature. But here there is a finite derivative. So there is no singularity here. And here there is an infinite derivative. So singularity is still there. There is an infinite derivative. Okay, anyway, this goes well beyond of my lecture, so there is a whole literature on that, very nice, but I only wanted to show you that there is a very nice theory associated with one-dimensional interacting field. Okay, good. So now I'm starting computing. So in the beginning, what we had? We had fermions. And as I told you right now, there is a Fermi momentum. So there is some dispersion relationship, let's say quadratic, for the fermions. And there is a Fermi energy, and when which depends on the density of particles. And when the Fermi energy hits the dispersion relationship, there are Fermi momentum. So of course here is 0. There are 2 points of the Fermi surface. So in 1D, this Fermi surface is 2 points. And then there are 2 possible processes. One process is when your particle is scattered at very large scattering momentum and is transferred from this point to that point, to the vicinity of that point. So it is a big momentum transfer. And the other process is when the momentum is changing, but in the vicinity of this point, or in the vicinity of that point. And this is a small momentum transfer, so slow evolution in the space. And so in order to take into account both processes, what people do, they say, let's consider 2 species of the fermions. So one which with the momentum close to to plus K Fermi, and call this right moves, because the velocity is like this and it is positive. And then additionally, another species of fermions which are near this point, and they are called left movers. And now there are processes of slow variation, some small momentum transfer, which is described by this field phi, and there are processes of coming from left movers to right movers where there is a large momentum transfer.
Sorry. Very stupid question, but still, this psi that we consider, this is
It is a fermionic field.
Fermionic field. So it comes from Kravtsov.
Yes, it is, or from any other one-dimensional fermionic model. So this is a fermionic field.
So this X is our previous E.
This X is our previous energy of level. So S.
Okay, and it is like an attempt to. And it is an attempt to solve it formally.
It is what I want to do. I want the following way. I want to represent. I want to what is called bosonize fermions. So bosonize fermions is to represent a fermionic field in terms of the bosonic.
Yes. But I want to think of the Hamiltonian that we have for fermionic operators. It is still that old Kravtsov Hamiltonian with.
Okay, think of Kravtsov, right? Okay. So even though this bosonization procedure is much more general, so we may take another one-dimensional interacting fermions and do the same thing. So so this is how to represent fermionic field in terms of boson. And basically it is the following, as I said. So what this phi can be considered as an addition to this K Fermi X. So there is a K Fermi X, the main part of the phase, and then there is additional part of the phase which essentially is the variation of the Fermi momentum. So if you do the processes close to this K Fermi with small momentum transfer, this is taken into account by this field. Since the Fermi momentum in 1D is related with the density, so Fermi momentum is proportional to the density in one dimension, then the variation of the Fermi momentum, this phi, is proportional to the variation of the density. So the description like this, it tells you this field is basically describing the variation of the density, so it's describing the sound, because the variation of the density is the sound, and therefore it is bosonic. Okay, now I want to do the following. So my goal is to compute density correlation function. For that, I have to express the density in terms of the bosonic field. So first of all, we know what is the density in terms of fermionic field. So forget for the moment about these terms. So this is the canonical form of the density in terms of the fermionic field. I will explain you this. So this is a canonical form. So what I have to do, I have to plug this relationship to here. and then what I will get the following. So first of all, as I said, if as I said, so this field can be considered as the addition to the Fermi momentum, and therefore it is addition to the density, but not literally the field, because what is Fermi momentum, the main Fermi momentum? It is just the derivative with respect to x of these fields. So the addition to the Fermi momentum is the derivative of phi with respect to x. And then the derivative of phi with respect to s, it really corresponds to the variation of the Fermi momentum, and the variation of the Fermi momentum divided by pi is the variation of the density. So we know that in one dimension the Fermi momentum is derived in the following way. So there is the phase volume, then the density is the phase volume. The density is the phase volume divided by 2 pi h. I need h here, and then since and then it is k Fermi by pi. If it is 3 dimensions, then there will be a volume of the Fermi surface, and then divided by 2 pi h to the third power. But in one dimension it is like this. And therefore, by combination of this argument, that phi is the additional phase due to the variation of the Fermi momentum, then the derivative of phi will be the variation of Fermi momentum itself, and if I divide it by pi, this will be the variation of the density. So there is one term like this. This is the variation of the density, which is related with this pi and with processes with small momentum transfer. But then there are processes with large momentum transfer where your right movers become left movers and vice versa. So this is obtained from the when I take this psi, put it here, and then in addition to such terms which do not oscillate, there will be terms which oscillate with. So when I combine this term with this term, then I will get non-oscillating terms. But when I combine these terms with the similar one with the same sign here, I will get oscillations with twice the frequency. So this is straightforward to get such two terms here. But the thing is that, as I have shown to you in the symplectic ensemble, there are two harmonics. So two harmonics of oscillations. And how to get two harmonics of oscillation? So if I only have this term, then all what I can get is 2k Fermi x and nothing else. But how to get an additional harmonics? And in additional harmonics appears, this is a subtle thing, but in fact when we do this bosonization, it is not as simple as it appears, because essentially what you do, you change the curved dispersion relationship by two linear paths. But you know, somewhere here there should be intersection, and there should be you know, some connection between these two, because it is present in the real dispersion. And this thing leads to anomaly when I only have such subdivision by right movements and left movements. Then I am getting some singularity, and this singularity eventually produces the terms of higher order here. Even though, you know, if you are in 3D and there is only this term. So this is a subtle thing, but it is present, and in principle there could be as many harmonics as you wish. But the coefficients here in front of these higher order terms, they depend on the initial model. So if you have the Kravtsov model, then this coefficient and all others are zero for the orthogonal and unitary ensemble, and for symplectic ensemble there are only two terms, this one and that one. But in principle you may have one-dimensional models of interaction where there are more harmonics. This Kravtsov is not the simplest one, because there is this in the symplectic ensemble, but still there are at most two harmonics. And then what we did, we expressed the density correlation function in terms of the bosonic field, and so when I do this, I forgot to say that in fact what appears is the combination of right and left here, because I mean, it's very simple. So if you take this dagger into account and you want to have oscillating term, you always have to combine right and left. Okay, so this is very trivial. So this you can do, I mean, and obtain on this form.
Yeah, sorry, but where the derivative term appeared from?
Huh?
Where did the derivative term appear from?
Once again, when I plug this
Yes.
R from here,
Yes.
I have an additional phase in addition to K Fermi X. Okay? This phi is an additional phase.
Yes.
Because there is I here. Now, then if I take the derivative of the phase,
Mm-hmm.
so zero order term gives me K Fermi,
Mm-hmm.
and the additional terms give me derivative of phi, right?
What do you mean?
I take
Okay.
the phase
yes,
is this
yes,
plus
yes,
that.
yes. Okay. Yes.
And so this additional gives me a derivative of phi. So this means that this derivative of phi is exactly the variation of the Fermi momentum.
Mm-hmm.
But the Fermi momentum always is proportional to density.
Yes.
Therefore, the variation of the Fermi momentum is proportional to the variation of the density.
Mm-hmm.
As simple as that.
Yes.
So everything which is here is extremely simple. The other thing is that there are subtle things like appearing of these terms. Okay, and then okay. So then I know what is this variation of what is the density variation of the density. This is a background density, And then I want to compute density correlation function. So I have to take this thing twice, and then do the quantum mechanical average. So, and what will happen when I do so? I will have the correlation function of gradient phi times gradient phi. This is one correlation function that appears, and the other one is the correlation function of cosine with additional phase. And correlation appears because this is some field that is evolving as free bosonic field. And so I need to have two types of different correlation functions. And now I'm going to compute them. So this is the density for free bosons. And I kept here the final temperature just to, it doesn't correspond to Wigner Dyson, but it will correspond to something else. Therefore, I keep this, temperature here. Now, I do the Fourier transform, but since it was, as I said, it was in a restricted volume, and that there is a boundary condition that the field at 0 should be equal to the field at 1 over t, then the frequency that appears that is conjugated to this imaginary time, it is discrete. And it is so-called Matsubaru frequency, which is 2 pi times temperature times n. When temperature is 0, it is continuous, it is not discrete. So this is just the Fourier transform. And then, if I know these coefficients, then I can find the field by an inverse Fourier transform, and eventually compute everything. So, okay, so this is the Gaussian field. The Gaussian variable is this A amplitude. It is a quantum mechanically fluctuating variable. And this is the inverse of that is the variance. So you know what is quantum mechanical average of the Gaussian field. It is an inverse of this, together with this factor. So I have the quantum mechanical correlation of this, the quantum mechanical fluctuation of this field. This is simply because this field is Gaussian, free bosons. And now I can compute any correlation function. For instance, let me consider the correlation function like this. And where n is some number integer. It is just for completeness. Now, again, what is known for about correlation function of such exponents if the action is quadratic? So what you have to do, you have to expand this. You should combine these two things in one exponent, and then expand formally in the infinite series in pi. And then you should take into account that for the Gaussian field, the average of the power of phi is decomposed by the product of averages. So if you have phi, then and the action is Gaussian, then there is a weak theorem. So there is phi, then again phi, and so on. And all the even all the odd averages are zero. So when you do such thing, you will get the identity, because you first expand, then you use the big theorem, and then you again sum what appears after the averaging, and you have exponential of this thing. So this is a very well-known formula. It appears in many theories of phonons, for instance. It is called the Debye-Waller factor in the theory of phonons. Okay. Anyway, so this is an exact thing, and then I need to compute this edge. So this factor, of course, can be taken out, and then what you have to do, you have to average the square, average with this correlation function. Then what I'm doing, I'm just representing it as the I mean, I didn't write it here, but okay. So there is, for instance, okay, when I change x by s, so you have in particular things like this, and then you have the average of phi x tau squared and the average of phi 0 0 squared. Since all the averages depend only on the difference, these two give some constant which has to be additionally computed. So what is the interesting part is when you have the double product of this field and that field, and this is exactly this this story, and this is of course a constant. And then what I do, I use this representation. And then let's consider tau equal to 0. So this tau is equal to 0. So this is a specific correlation function, equal time correlation function. And then temperature 0, which eliminates this discreteness. It becomes not discrete. So then the sum, which comes from here, then the sum is converted into integral because temperature is 0. And then you compute this omega integral, and it is 1 over modulus of k. And then you have to, in order to compute this correlation function, you have to take this 1 over modulus of k, the function is even, therefore I take from 1 over to pi, and then I have to compute this thing. And this thing is convergent because of this difference, and it is essentially the following, that when k when k is large, I can forget about this cosine factor, and it will be 1 over k. It gives logarithmic divergence. But when k becomes small, this cosine factor should be taken into account, because eventually 1 minus cosine for very small k becomes 0, and this makes the cutoff of this logarithm. So this g is indeed logarithm of s with such a prefactor. And then I introduced already this g, which is a logarithmic function, and now I have obtained that it is a logarithmic function. So this integral is exactly this g from the previous slide. And then if I collect everything, then I'm sorry, here I have to put tau equal to 0. So it is tau equal to 0 and temperature equal to 0. So correct, this tau is 0. And then I have this correlation function which depends on this interaction constant, which depends on the number of harmonics. Yeah, it stays here, and this g, which I have already introduced. And then if I take the smooth part, I compute such a correlation function, and it becomes the second derivative of the same g. So now I have all the necessary ingredients to compute the density correlation function. So I use this stuff, and then I use the result of what I have shown to you, and eventually what I get the following, that non-oscillating part of density correlation, it is the second derivative of this g, and then I can say what is k, because if I know this non-oscillating part, the non-oscillating, and I know the answer. The answer is this. So I know this non-oscillating part, and the coefficient here should be equal to this coefficient. And it depends on beta, because this is beta equal 2, beta equal 1, beta equal 4. And when I compare this thing with that, I see that k is 2 by beta. So for this particular Kalogero Sutherland stuff, which corresponds to this correlation function, k is equal to 2 by beta. So as was expected, when beta is 2, it is non-interacting fermions, and k is equal to 1. When b is equal to 1, the k is equal to 2, and this corresponds to attraction. And when beta is equal to 4, k is 1/2 smaller than 1, and this is the repulsion. So everything as it should be. And then when I look at those oscillating parts, I see that those oscillating parts are actually of this form. So you can take the Fermi momentum is like this. So you can take, for instance, beta equal 2, then k is equal to 1. Then this 2 pi s is 2k Fermi s, so it is just first harmonics. So n is equal to 1, and k is equal to 1, so I have exponential of g, exactly. I have an exponential of g, so for n equal 1. Now, if I go to orthogonal case, then it's again first harmonic, so n is equal to 1, but now k is equal to 2. And I have indeed 2, so this is just k for orthogonal case. And when I am in symplectic case, I have different fermi momentum, and I have two harmonics. This is the first one, and this is the second one. So for the first one, n equal 1 and k equal 1/2, I have g over 2, exactly, g over 2. So you see that I have demonstrated that the correlation function is indeed given in terms of the free boson field at t equals 0, and this is when I collect it all together, I find this cluster function in this form in terms of bosonic variable. So everything is expressed in terms of these bosonic correlation functions, and the only structural constants are these. And this is indeed the place where I know that there is a collision Sutherland with corresponding interaction. This gives this constant which are like this. So this is specific to collision Sutherland with the corresponding interaction. And then of course each of these correlation functions depends on k, and k is equal to 2 by beta. So we have a complete correspondence between the theory of free phonons and of interacting fermions and the Wigner-Dyson stuff. So I suggest that you compute all these things, and if you have difficulty, I answer your questions. So basically, this is the last thing. There's nobody. Okay, so this is the last thing. So again, this correspondence that I shown to you, it is the again, and this should be equal time correlation function. I have copy pasted it. Tau should be 0 because this does not depend on tau. And this is correct, but here I copy pasted not correctly. But what I want to say that this is the theory which is in terms of equal time correlation function, but not equal space, and at 0 temperature. Because when we calculated, we computed the integral of that in terms of instead of the sum. But if the question is, what will happen if I am just curious, what happens if in this theory when the temperature is non-zero? Of course, it is no longer Wigner-Dyson, it is no longer ground state of Kravtsov-Sutherland, but what will be? Because the theory which I did, it is very easy to generalize. So the only thing is that I have to have a sum instead of the integral at 0 temperature. And this sum is exactly doable. And what I have, when I did integral, I have 1 by k. And here I have, so cotangents hyperbolic. Here should be cotangents hyperbolic. Cotangents hyperbolic of k by 2t. which at zero temperature tends to 1. And this was the result at zero temperature. And now, what I have to do, I have to take this result with corrected cotangent hyperbole, and then do the integration over k. Practically I tell you how it should be done. So this is an integral that is exactly doable. So what you have to do, you have to first differentiate with respect to parameter, the integral of the dk. You have to differentiate with respect to the parameter y over 2.